Okay, so good morning. So welcome to today's first session of Brown's winter AI Winter School. So this session we carried out, Lazar and myself. So this is focusing on graph neural networks and developing and deploying graph neural networks in particle physics. So we have like a first part is more on the theory, the scope, the motivation, and the importance of these techniques. And we also have a hands-on session using collab notebooks. Okay, so I guess you can see the slides, so and you can hear me. So first things first, what is a graph? So a graph is a mathematical structure that we use to model a relationship between points. These points could be objects, could be particles, could be measurements, etc. You will see later. And consist of a set of nodes or vertices. These are the blue circles here. These could be particles, for instance, could be the stars of a galaxy, and so on and so forth. And each node can have a set of properties or features in the more data science language. So, and this can be viewed as coordinates of the nodes, can be X, Y, Z, so spatial coordinates. So you can add also information about the energy of the particle, etc. And then consist of edges of connections that are the pin lines here. They are connected. Okay, now, and we can summarize the more elegant form. Here we have a set of vertices and a set of edges. Now, mathematically, this is represented by the adjacency matrix. I'm having this information here for completeness, but main point here is that when node 5 and it's node 4, we put 1. This forms an edge. If they are not connected, like for instance N5 and N1, we put 0. Okay, but we can have also a weight, for instance, values between 0 and 1 that in some sense represent the importance, the relevance of this connection to the problem we want to solve. Okay, so this is the adjacency matrix. So now, graphs are powerful math structures to model relationships, but this is not enough just to represent the data as a graph. And here is where graph neural networks come into play. So real-world data have very complex relationships, and traditional machine learning techniques typically to handle, to properly process and identify patterns in non-Euclidean data. So actually, graph neural networks can extract features relationship from graph structures. So the core idea is the nodes that I showed earlier can exchange information between them. This is called message passing. We can have transformation of the features, the properties, the properties of each node to another set of features by using for exploring information of the neighboring nodes. And then this graph can be actually updated, so there is information that flows across the graph in order to capture longer range relationships. Now, in this lecture, we will give you with Lazar an executive summary of the LHC experiments. We are going to discuss why graph neural networks in particle physics transform the field. And then we are going to have two tasks using graph neural networks. One is for classification, discriminate, separate between different particle species, and the other is to use graph neural networks to cluster. So we have deposit measurements on the detector, and we want to group, to cluster these deposits that come from the same particle. Okay, so this is the Large Hadron Collider. So it's located in the Geneva area. This is Switzerland. This is France, actually. This is the pink line is the Large Hadron Collider. Around back in 2012, there was the discovery of the Higgs boson. Here is the Lake of Geneva, the airport of the Geneva of Geneva, and this green line here is another accelerator where 40 years ago the W and Z boson, the mediators of the electroweak force, were discovered. So this is the largest particle collider in the world. The perimeter, this pink line here, is around 27 kilometers. Okay, and we used to bend and to collimate the beams, the proton-proton beams that run in opposite directions along the pink line. We use magnets at 8 Tesla, almost to absolute zero, cooled down to minus 271 degrees of Kelvin. And we collide particles 40 million times per second. Okay? Now, and there are 4 big experiments: ATLAS, CMS, ALICE, and LHCb. And this is a cross-section of one of the experiments, the CMS. You see that we have the different colors here corresponds to different detectors. So you see that there is different patterns, different signals in each of the detectors, so that the detectors are very heterogeneous. Okay, so this is something we need to have in mind. And this is when we collide particles, every time we collide particles, this is what we see. So the different colors correspond to different signals, in different parts of the detector, so in different parts of these various detectors here, okay? And what we do is actually we want to combine the information. We find the relationship between the signals in different parts of the detector to what we call to reconstruct the event, and then come out with a particle, for instance, the electrons. I'm sure you have heard about it, muons, photons, and other particles. Okay? Now, this is the coordinate system. So we are going to discuss, so this dust line, black dust line here is the beam, right? So you have a bunch of protons coming from this side, and another bunch of protons coming from this side, and they collide here in the center at 0, 0. The z-axis is in the direction of the beam line, the beam pipe, and then we have the x and y axis. The x points towards the center of the LHC, the y-axis towards the surface, and then we have the angle between the x and y is what we call the azimuthal angle. You are going to see this in your exercises. And then we have this theta angle, which is an angle between, with respect to the beam pipe. Okay? Now, this was an executive summary. I mean, we don't have time to go into details, but the important is to get the key points. Like, imagine if you drive a car, you need to know how to turn the wheel, don't mess up the acceleration with the braking. So, but this is what we need. We need a few things to have in mind to understand why graph neural networks are important. First of all, we're talking about high-dimensional and very sparse data. So these detectors are huge. They have more than 100 million channels, right? Sensors, signal. Not all of them provide signal in every collision. So it can be different parts and oftentimes distant parts of the detector. So we have complex events, high-dimensional, and many regions, large fractions contain little or no signal. So we have sparse data. We have heterogeneous events. We have different types of detectors. We have different types of particles that give different types of signals. So we have to develop algorithms that are relevant and powerful to identify all these different signals. We have long-range dependencies. So the physical processes involve relationships between distant regions of the detector. Okay, we want to explore, for instance, correlations between particles that travel in different directions. If you go here, one particle could travel here, the other particle would go this direction, but those can come from the same parent particle. So we want to exploit their correlation. So at first sight, they're distant, but in terms of relevance and importance for the task we want to do, they could be, they have like strong relationships. So we want to explore them. And then we have like a complex topology, right? We produce many, many particles. You see this mesh here, and we want to identify particles within this mesh. Okay, So the advantages of the graph neural network is, first of all, flexibility. So when you have a graph, you don't impose a fixed structure on the data, like, for instance, we do in convolutional neural networks. And we're going to develop also a two-dimensional convolutional neural network so you can have a direct comparison with and appreciate the advantage of graph neural networks with respect to convolutional neural networks. Those, the GNNs, the convolutional neural networks, operate on regular grids. The other thing is that we can exploit local patterns using graph neural networks. This is the same also as we can do with convolutional neural networks. Okay, and also they are more efficient. So compared to the fully connected or dense neural networks, graph neural networks have much fewer number of parameters that has to be optimized, because the graph neural networks focus on relationships between the input data that actually matter for the specific task, for the specific problem, and ignore the irrelevant ones. Okay, so in particle physics, graph neural networks in particle physics, as I said at the beginning, but let me highlight it once more, the nodes of the graph, the blue circles here, could be particles. So if you go into this event display here, collision event, each of these colors here could be a node in the graph. Okay, each of these guys here, the greens, the blues, the orange. Okay, it could be also even lower level, just detector signals, etc. Then we can have information properties of its particle, like the x, y, and z, the coordinate system, the spatial coordinates, x, y, z. We can include information related to the energy. We can have information related to what is the type of the particle. If it's an electron, it's a photon, or a heavy electron that we call a muon, and so on and so forth. And then, depending on the problem, and this kind of art, how you are going to represent the problem, is establish connections between these particles. So if you have questions, feel free to interrupt. So the first exercise we are going to discuss, let me give you some background, is we want to classify, to separate, to discriminate between different particle types. So without going to the physics very much, usually, since we collide protons, that kind of particles, we produce other particles that cascade, they create a cascade of secondary and tertiary particles. So these are the green lines that you see here. So the big question, one of the biggest and most fundamental question, is to understand which is the type of the particle that initiated the formation, the production of these green lines here of the secondary and tertiary particles. Okay? So what we do is we define an algorithm that groups, that clusters these green lines here, these particles here, and look the relationships between the green particles and try to infer the type of the initial particle. So this is a classification. Think about if you have a cat and a dog, you look about the size of the objects, how the ears look like, the eyes, the nose, etc. Well, we don't have eyes and ears and noses here, but we have relationships and correlations between these particles that can actually give us information about the flavor, the type of this initial particle. Okay, so this is called it. And just to give you a feeling about the scale, each of these green lines here, the particles, has something like 50, each jet, this orange line here, we call it jet, this cluster of green particles, has something like 50 to 100 green lines, particles, right? Depends on the type of the initial particle. And each of the green lines has something like 50 properties, features. So when we want to do classification, that type of classification means that we have to process order of 1,000 inputs for each of these jets. And we can have tens or more of these objects for each event. And remember, we collide, we produce we collide the beams 40 million times per second, okay? So the basic things for those that are more into particle physics, just a high-level discussion, is we want to understand, for instance, if these particles here, if these green lines here are produced exactly at the collision point, or they are produced a bit further away from the collision point. So this can provide very useful information. Or if you have also tertiary particles that are produced even further away from the collision point. So this is useful information. The other thing we want to see if there is some substructure, if you have like subclusters of green tracks within this object that we call it Z. It can be just, or the entire energy is in, we would call it one prong, or we have two subclusters or three subclusters and so on. And the other thing is, of course, the mass, because if you have a particle and you cluster all the decay products of the particle, then the mass of this object will be the mass of the, or close to the mass of the initial particle. And this is what you see here. I'm sure you have heard about the Higgs. The Higgs has a mass around 125 times larger times the mass of the proton. And you see that if you collect all these particles, you have like a mass of these objects around the mass you expect. So these are all useful information. And the key question in AI and machine learning based algorithms is how you have all this information, how you represented it. And what happened at the beginning is to treat the detector as a camera, okay? And then treat the jet, this object, as an image. And process this information using convolutional neural networks. We will see how we develop this. But then the most recent development that, as I said, they transform effectively how we do data analysis at the Large Hadron Collider is to represent the jet as a graph that we discussed earlier, and then use graph neural networks to process the inputs. And then we're going to develop these algorithms for classification and then compare the performance of those, a simplified version of those algorithms. Okay, so let's start with representing the jet as an image. So this is this guy here, but now it's in 2 dimensions in the X and Y plane, or the X and Y plane. So here you see there are 3 clusters of points. So we are talking about discriminating top quarks. The top quarks decay to a W boson and a bottom quark, and then the W boson decays to 2 other quarks. So we have, you can see by eye, we have some like 3 subclusters of particles inside this jet. Okay, so we treat the detector as a camera and the jet as an image. This is an image, and then we apply techniques like we develop a convolutional neural network. So the idea is we apply different filters. This is what you see here with boxes. The different colors corresponds to different filters. So each filter is trying to identify different patterns inside this image. So think about cats and dogs. There is different filters that identify edges, other filters that try to identify more rounded, like nose or the mouth, etc., etc. Right? So we run, we slide the filters across the image, the different filters across the image. And then we have a set of 2 dimensions, this is a 2D image, a set of convolutional layers, where we can stack effectively the information extracted from each filter and create a set of layers with different sets of features extracted from the initial image. And this can go on and on and on. Then we have a step that is called pooling. So effectively we define an area in this image after the first or second or n number of convolution, and we pool information, we aggregate information. We can find, for instance, let's say we have a 2x2 pooling operation, and we find the maximum value of these 4 squares, or the minimum, or the average, etc. And we do this to improve the robustness, because there could be some fluctuations, or it could be some malfunction of the detector. We don't want to rely on subtle information. And also we reduce the dimensionality. As we see, this 2x2 became just 1 pixel after applying the pooling layer. And then so we extract here up to here, we extract features, okay? Ears, noses, eyes, etc. And then we want to correlate, to find the correlation between the extracted features. And here we do it with a simple dense neural network that I'm sure you are all very well aware of. So you have like here this inputs, and its input here is connected with the nodes, these boxes here are nodes of a fully connected neural network. And the output can be a binary classifier, like it's a cat or a dog, or it can be a cat, a dog, and a horse, etc., etc. In our case, we're just going to have a binary classifier. Okay? Now, maybe I can stop sharing the slides and go to the notebook. And while I'm getting there, I'm happy to take any questions you may have.
So the first, well, simple question first. What type of correlation function are you using? I think this was a reference to somewhat earlier in your presentation, but I think we're just asking.
So we don't explicitly, yes, so we don't explicitly, I mean, depends how you do it, but you can actually, you can either let the neural network figure out the correlation by applying weights between the connections, and then these weights are updated via backpropagation, right? Or you can, again, can go back to the graph. You can, for instance, here, when you form, for instance, the edges, you can say, okay, I want to see the difference in the momentum or the difference in the distance, and you can be more explicit. Usually, when you inject physics knowledge, you know kind of what you expect. It makes the training and the easier of the algorithm and the performance better. Okay, because we don't have infinite data, we cannot have an infinite deep and complicated algorithm.
Thank you. Because actually, could I, obviously we know you're coming in from a remote site. It might be worth you turning your video feed off just to maximize. Okay. We're getting some interruptions, and that's great. So obviously we'll share your screen, but I think we'll maximize the focus on the audio. We appreciate you coming in from remote locations. So there was a question specifically about when you talk about tagging, do you mean labeling, and does this depend like math?
Yeah, labeling, I mean identification. Saying like you tag an image, you classify an image as a dog or a cat, or as a one particle or another. So now I have also the Q&A. I don't know, shall we go over? Okay. The last one, can you explain what is the value of each pixel in the image? We will see in the exercise which value we put in its image, in its pixel, the value in its pixel. So based compared with those from the addition, it's yeah. So I don't know. So shall we answer now, Greg? What do you think? Shall we answer now all the questions, or?
Suggest you move to get people working on your notebook, because that'll take a little while for them.
Okay. Yes, let's start setting up the notebook, and I will come back to your questions, guys, because in some cases we may need to. It will take some time to to download some packages, etc. So let me share the notebook now. So I assume you all have this notebook ready. Maybe I can zoom in a bit. Can you see my screen well, or shall I zoom in?
The screen, if you want to zoom in a little bit more, you can, but it's perfectly readable for me.
Okay, so let me, so here there are more information. This is also meant for offline reading, and maybe, if something, because you have an avalanche of information, different modules. So this is, you can go in peace and and read them. But the main point here is we want to compare, and this was one question in the Q&A, to compare the performance in, for instance, a classification task, like identify different types of particles. We pick 2 in this case, between convolutional neural networks and graph neural networks. Okay? I'm taking this opportunity to answer another question, that how it compares between different more traditional ML techniques. I didn't include it, but I can tell you that it's a game changer. So for the same signal efficiency, meaning true positive rate, the false positive rate, the mistag rate, using graph neural networks improves by more than an order of magnitude, a factor of 10 or more, 20 or 30. So it's a huge difference, huge difference. So, okay, this we discussed. Now, the key steps here is that we are going to discuss how we load the data and how we do pre-processing, and this is, the pre-processing depends on the algorithm, the representation that we are going to choose. Then we're going to discuss about the model definition and how we train it, and then we're going to evaluate the performance. We will use one metric, the receiver operating characteristic curve, which is effectively has in one axis the true positive rate, the efficiency, the signal efficiency, we have a signal, and on the y-axis the false positive rate or the mistag rate, okay? The rate that wrongly identified, let's say, a dog as a cat, when the true is a dog, let's say, okay? So, so we have a data set. You can find information about the data sets here. As I said, these are details, and let's skip some technical details for now. We have a set of inputs, of examples, of training examples that have two different set of particles. For those that do particle physics or physics, top quarks and up and down quarks. But it doesn't matter. Two different types of particles for those that don't really care about those details. Okay, so we load the data set. So, and we have jets inside, like I have objects that we cluster, we group the secondary and tertiary particles. And what we are going to do is we are going to use information, in the interest of time, just 4 information associated to each of these green lines in my presentation. So it will be the transfer momentum, let's say the momentum of these particles, the rapidity is effectively related to the angle between of the particle where is emitted with respect to the beam pipe, and the azimuthal angle, it's in the transverse plane. This is shown in the slide that we discussed earlier, and the energy and the total energy of the jet of this object. And then we have also labels that indicate if the jet is one type or the other, signal or background with 0. So okay. So this, the first part is to include the H5Py library. This we use it, we needed to load the dataset. NumPy is the usual, a very common and extensively used Python library, and matplotlib, we will use it to make some plots, okay? And then because we use Google Colab, we have to mount the drive. Okay. And the information, and this is the path where you can find all the information of this, well, the information about this year's winter school, and here, sorry, is the path to the material that you will need to run the exercise of this module. And this is the input file. It's a small one because it's just 10,000 training example. Of course, this is very small, but it's enough to make the case and have something that we can run within the time we have here. So, in this part, so as you said, we want to use information like the energy of the particles and the energy of the jet, etc. So this is the way we use NumPy and we create an array of, we read the root file and create an array of the momentum of its constituents per object, per jet, the eta, phi, the energy, and so on, and the labels. And on the question from some of the students or some person about what we put in the pixel, and you will see it later in the plots, is because we don't want the algorithm to separate based on the momentum of the object rather than what's going on inside the jet, we normalize the energy of each particle is normalized, so we divide by the energy of the total energy of the jet. Okay, so this goes the value on each box, the color is from 0 to 1. It cannot be each particle, each green particle that you saw in the sketch cannot get more energy, cannot have more energy than the entire object, right? Okay, so this is normalized. And here we're going to use one channel, like 2D CNN with one channel, one color, okay? And this will be the relative energy, the normalized energy of its energy, of its constituent, of its particle. Now, first things first, we want to see if the classes are balanced. So here we make a plot that shows the relative fractions of background and signal events. We have two types of events, so it's binary, yes or no. So you see they're pretty balanced. This is good. Okay, we don't want to bias, or at least a priori we don't want we want the training to give the same importance in both the background and signal output. Now, because those are probability, and particularly when you have a multi-classifier, you can change these probabilities a posteriori. The other thing is because we may have a very important thing is how to pre-process, how to filter the inputs, and because we may have like malfunctions of the detector, or the event reconstruction failed for some reason. A simple filtering that we are doing here is to say, okay, ignore particles that have exactly zero energy or momentum. Okay, because there was probably, maybe it was a region that was the sensors on the detector were not working there. Okay, so we do this filtering, and here we want to plot the distributions of the input features. So this, you run the code here. Sorry, that was not expected. Because I didn't run this. Yes, now it should work. So you see two colors. With blue is the signal, type 1. With red is the background. So here on the y-axis is the log scale. So these are the zeros. I didn't apply the filtering yet. And you see here there's not much discrepancy, difference. Here there is some difference. Here much less. Here, which is on the bottom right, which is the normalized energy, and you see it goes up to 1, close to 1, as expected. This is good validation. There is some difference. But the key point, I mean, if they were really very separated, you have a cluster of blue here and a cluster of red here, we don't need the neural network, right? We will apply a straight selection and separate them. The key point here is that although by comparing this one-dimensional distribution, you don't see a difference, the neural network exploits the correlations between these inputs and can separate between different types of particles. And here is the masking that I discussed. We reject, we filter out cases that have no energy. Okay. Now, this is in general something we do for both the CNNs and the graph neural networks. Now, let's start building the convolutional neural network. Now, because the jets are produced in different directions, it can be in different directions. The detector, we don't want that separation to depend on the direction, because this, at the end of the day, is the same jet, is the same object, right? Class 1 or class 2, we don't want to depend on where is exactly produced in the detector. So what we do is we center the object, the jet, at 0, 0 when we want to form the image. So we renormalize, to make it independent on the direction that the particles are produced. What at the end matters is the relative difference between the particles. So this is what this complicated code does, but you can read it, you can go through it later and understand. But the idea is that it actually centers the jet, each object, its input, its train example around 0, 0, and then it does some wrapping because the angle, that the phi angle that we discussed, it's symmetric. So minus pi and pi is the same thing. Okay, so we run this. So this is not AI, this is pure Python. Okay, so we did this pre-processing, and then let's see what we did actually with this pre-processing. So we're going to plot the the image before, like all images, all objects, all jets, before and after the pre-processing. So this will take some time. So I will run this, and I'm going to go through the Q&A now. Okay. It should be in the drive. So the question should be the drive. I use the drive, I just put a temp. This is what is in the drive now. Should be in the drive. So you can see here. This is in the drive, I just copied this so I don't mess up the drive one. Now, ignoring particles have zero energy, remember, can they be taken as a background? No, we ignore them both for background and signal because, I mean, this is not a very involved filtering, but we ignore them because this could be like in a region that we didn't, the detector could be like not operational. Signal and background class, for in this case, signal are what top quarks is a type of particles. Background is another type of particles, up and down quarks, and they have different properties, and we want to use these different properties to discriminate between them. Since my set drive disappeared, where do I find the Google group? Okay, this I don't know. How do you connect CNN and GNN part? You will see this later. How does the results from CNN and GNN based approach compare with those from the, this we answered. Okay, so this is what we have here. So now you see my screen, right? So on the left is before the pre-processing. So you see there is a mess here. You cannot discriminate because the jets are produced all over the detector. Now with this pre-processing, we center around 0, 0, and so we don't rely on where actually the jet is produced, rather than what is the difference, the correlation between the particles. Okay, so things look good. And the next step is the more AI, more technical part, is we want to start creating the PyTorch tensors. So we want to start creating the images. This is purely technical. We create a 2D image, in the theta angle and the phi angle here. And then, because when we start reading the input files, we created arrays, and the fourth actually feature is the normalized energy. So this is all the thing that this guy does here. And then, because, as I said, for simplicity, we want a single channel, so we want one channel, one color, and the color here, the intensity on the z-axis, this is log scale, should be only the normalized energy. We just create an image, CNN with one channel. Okay, so this is the X tensor. Okay, so these are the images, there are backgrounds and signal, and we already know, we have the labels, the information about which one is signal and which is background. And then we have the Y tensor, which is here, holds the labels, so we can do the back propagation. So of course, those arrays need to have the same length, right? So you can connect one image with a label. And this, we create the tensor data, so we use PyTorch here, and we split the 10,000 events to a training set of events, 80% of them training events, and then the remaining as a test event. And this is just pure PyTorch stuff. We will create the loaders, the data loaders, the training and the testing. And here, this is the batch. It means every time we do the stochastic gradient descent, how many of training examples, how many cats and dogs, or how many signal and background images we're going to use. And this is 32. This is not optimized. You can play. I encourage you to play with these values. Okay, so let's run this. Should not take much longer, too long. And then, so here, what we do is we define, in the interest of time, we know that typically this is the region that the jets are not, these objects, the particles are not they are contained between -2 and 2 in these angles, in these variables, and -1.5 to 1.5. So what we do is we set this range, this distance in these ranges, and then we create pixels. So, because we want to have an image. So, just to go fast, we split each axis, this range, we divide by 10. So we have 10 by 10 image. You can do 80, 40, whatever, right? Okay, here is more granular, but it takes much more time. So for this exercise, we split in by 10. It's a 10 by 10 image. Like this. And here we built our neural network. So this is the, we have the CNNs target. So we have the first convolutional layer. So let me walk you through. Here we have one channel. So this is the input channel. It's one color, right? Its pixel has, the value is the normalized energy. And then the output, we want a 32, okay? And then the filter, again, these are not super optimized. I encourage you to play with this, is a 3 by 3. So we go, so since we have a 10 by 10, we have a 3 by 3 filter that slides along the image, okay? And then we do padding, because just, probably you are aware about this, but just a reminder, when you start going to the edges, you may not, you cannot have a 3 by 3. You don't have 3 pixels to run for the filter to glide. So what we do is we add another pixel and we put a value of 0 there. So we can run the convolution also in the edges. And then we have a second convolution layer and picks this 32 image to 64. And we use the same kernel and the same padding. And then we do a max pooling, so with a 2 by 2. So you remember on the slides, we find 2 by 2 squares in the image after the second convolution layer, and we have a new image where we select the pixel, the value with the highest, with the maximum value between the 4 pixels. Okay, and then we do a flattening, because we extract the features, and you remember from my slides, we want to explore the correlation between these features. So we flatten, and we do 2 linear layers, 2 fully connected neural networks. And since we have a 64 here, we multiply by the number of bins, etc., and we have 128 hidden layers, and then we have a second hidden layer, 128, and because we have a binary classifier, the output should be 1, yes or no. And this is passed via the sigmoid, okay? And here are the activation functions. So the details are here, and I'm happy to discuss any questions you may have. So let's run this. More or less what I said here is also written here. And then we define the model, and then we want to see if we are going to run it on GPUs or CPUs. So this line here, CUDA, is for GPUs. If it exists, it will use it. It's much faster. If not, we use CPUs. And we deploy the model on the device. So the code as it is can run both GPUs and CPUs, and you don't want to take any actions. And here it's just to have a look about the model. This is how it looks. Okay, so you do it and you cross-check it, and here you can also have a feeling about how big is your model. This is a very simple one. We have around 50K learnable parameters, and this is information about the input size, the output size, etc., etc. Now, this is very simple, very light network, but when you build a very big one, you want to understand if your computing resources, the computing resources you have, are sufficient to hold this neural network. So we run this, and then we want to train the model. So the training happens, the learning happens using the loss function, okay? So effectively, we compare, because we do a fully supervised training, we compare the prediction from this network, the output from this network, with the truth, with the true information, okay? And we use the binary cross-entropy loss. So this is the prediction, the y tilde is the hat, the y hat is the prediction, and y is the truth, the labels. And you see it has this form because what it does, what it wants, is it wants to penalize predictions that are very bad. So if you have a class type 1 and it predicts 0, if you put it here, you see it adds a very large value of the loss, and it puts more importance on these cases. Perfect prediction means the loss function is at 0. So the goal is when we do this several times, so when we run and we train every time through going over all training example, in this case the 10,000 or the 8,000 objects, we want, and this is called an epoch, we want to start to, if the algorithm learns something, we see this loss function to getting smaller and smaller and smaller. So this is what we're going to do here. So we run for 4 epochs here. Let me go in, this will take like a few minutes, so let me go to the Q&A. I know there exists preprocessing library. Look, the preprocessing libraries, for CNNs is more involved the preprocessing and depends on the problem. If you really want to push the performance, you have to customize it. We are not going to discuss this here, we don't have the time, but you can cap, you can actually use percentiles, not the mean and the standard deviations that the scikit-learn has, etc. So you have to, preprocessing is very important. Long story short, preprocessing is very important. Now, on the other question about flatten is effectively to make the 2D in one dimension. So if you have like, let me just for a second open, turn on my camera, my video. So you have the 2D image and it goes like this. So effectively you start reading and make this 2D image, you unroll it to one dimension. Why do you see it based on the lead part and not? Yeah, there are, I mean, even this is a simplified, you can center it around, for instance, the leading the most energetic particle. There are many ways. This is, as I said, it's an art. Could you explain again what max pool do? So what max pooling does is you have these feature maps, right? After running 1, 2, 3, 10 convolution, it doesn't matter, okay? And you say I do a max pooling, a pooling of 2 by 2. This is what we do. So 1, 2, 3, 4 pixels. This you do it across the entire feature map, for all feature maps. And let's say we are now at this point, there is a value here, 10, 20, you know, 0.2, 0.9. If we do max pooling, we look which pixel here in this feature map has the highest value, and you create a new map, a new image here with the maximum value of these 4 pixels. You can be the minimum, can be the average, for instance. Okay, yeah, so I'll do the weights update with its buds. So, well, it could increase or decrease if you put 10. It could be a statistical fluctuation. You have 10,000 samples, It's a very small number. It could be the learning rate could be small, or it can enter in a local minimum if it doesn't improve, or if it's very large, it can so so you can have, imagine you want to minimize a minimization problem. So if you have a very large learning rate, it can start bouncing around but never go to the global minimum, and this can, after some epochs, it can actually lead to an increased value. But I believe in this case it's mainly statistical fluctuation. It's 10,000 bends. But what you can do actually, if you can actually decay the learning rate, reduce the learning rate as a function of the epoch number. How do the weights update with its bats? Are all the bats equally weighted? Yeah, this is actually, this is a stochastic gradient descent. So effectively you create these batches and you get the average of all batches. So they are equally weighted, yes. Not really. I mean, but you have to decide how, depends on the problem, you have to decide the batch size. So there's no information loss necessarily, but depends on the problem, you have to decide choose on the batch size. So this kind of trial and error. Okay, I think let's go on and we can discuss further. So this is we just run for 4 epochs. The loss function is 0.68. Okay. But we see it starts decreasing, so let's plot it. So we see indeed it's probably is learning something, okay? And then let's actually plot the ROC curve that we discussed earlier. So as we said, in the x-axis is going to be the true so first we plot the output. So here, this shows the blue is the signal, the red is the background. You see the separation is not great. Keep this in mind when we do the graph neural networks. But okay, maybe we had to spend more time on the neural network to learn better the features and improve the discrimination. But this is the output of the one class and versus the other class. So there is some separation, but unless we create the ROC curve. So on the x-axis, we put the true positive rate, the signal efficiency, the y-axis, the false positive rate, the background efficiency or background rejection or the mistake rate. The dashed line here is if the algorithm was learning nothing, random guess. You flip a coin and you close your eyes and you say this is a signal and this is background. So you have 50% for 50%, let's say, a true positive rate, you can have 50% background. So it's a random guess. This is actually better, and you see the area under the curve is not 0.5, it's not 50%, it's close to 60%. So it's learning something. Okay, now we saw how it works. We have a working example that where we represent the jet as an image. Now we are going to represent the jet as a graph. So reminder, each point, each vertex, each node in the graph is a particle. So we form a point cloud or a particle cloud. It's a permutation invariant representation. Here we have the features per particle in its node, and then we build the connection, the edges, the relationships that we discussed. Now the question is how you are going to build connections. There are many ways you can connect everything with everything. It's a fully connected graph. This is perfect. We exploit all correlations, but this is computationally expensive. For simplicity, this is what we're going to do here because it's a simple problem. But other techniques could be to, instead of connecting every particle with everything, you can develop an algorithm, a choice, a rule on how to connect algorithms. For instance, you can select the closest neighbors, use the k nearest neighbor algorithm. So you have this, we said this feature, this property, these are coordinates. So you calculate, for instance, the distance between each particle and those in this 4, 5, 6, 10, 50 dimensional space, and those that are closer, okay, they are connected. And this kappa means you want to connect the 4, 5, 10, 32, 64 closest neighbors. Okay? And then we build the graph, and then we have to learn from the graph. And as we did with convolutional layers, we follow a hierarchical approach. So we first explore local structures with the filters, and then we have this flattening to explore the correlation between these features. So we go from local structures to more global ones. And this we can achieve with convolution, with the convolution operation, which is, in the case of CNN, we have a fixed grid, and we have this filter here, and we glide across, we slide across the image, and we perform the operation. But when you have a graph, this is an unordered set of particles. So it's not straightforward how you can apply the convolution. Okay, and also the convolution operation, in principle, is not permutation invariant, and this is something we have to respect. So one technique, you can find more information here on the slides, is that we build a graph. For instance, we use the 10, let's say, closest neighbors, and then we define a function. This actually, we do it using multi-layer perceptrons, like a dense neural network, to extract features between the nodes, okay? So when we form the edges. And then we define a function that aggregates the information between, from what it was learned from the edge feature function. And this, because the convolution operation has to be permutation invariant, has to be a symmetric function. And for instance, you can get the average, you can take the average of the average value of each feature extracted by this multi-layer perceptor. So you can think about here, you have a neural network, simple dense network. Okay? Now, and then, because you, as we said, we transform, these are coordinates, we transform from the initial set of coordinates, from the initial set of features, to a new graph which has a better set of features that that improves the discrimination. So this is what we are going to do in the graph example here. A simplified version, as I say here in June. So let's develop the graph neural network algorithm here. Run this thing, we have to include some packages. PyTorch Geometric is it's a package that makes developing graph neural networks pretty straightforward. So it will take a few minutes. So in the meantime, I'm going to look if there are any questions in the Q&A session. In the max will do. Sorry, I see 21 answered. Sorry, are there any open? I see that there are 21 open questions, or is this? Okay, what if signal, blue one, is more than the background? How does it affect the correlation? You mean when you train an algorithm? So if you have more signal than background or vice versa, it means the algorithm will use more examples, signal examples, to optimize the weights. So it will put more importance on the features of the signal and less on the background. So this will affect the performance in principle in the binary classifier. Now, if you have a multi-classifier, you want to separate between 3, 4, 5, and depends on your analysis, you have 5 output classes, and the 4th and the 5th are not relevant. You can still either, before the training, put more weight on the classes that are more relevant for your problem, or if you normalize them, you have equal fraction of each class. You can treat the outputs as probabilities, and since these are probabilities, you can reweight them as long as you preserve the sum of the reweighted outputs to be 1. So the advice is to when you train is to have tip for most of the problem is to have equal number of events. Not when you generate, but you can apply weights. I mean, sometimes when you collect the input data set, you have more signal than background, but then you can apply weights that equalize them. You have the same fractions. Okay, so did this setup here. Now the preprocessing the graph neural network is simpler. So the only thing we do here, I mean, it can be more involved, but the only thing we do here in terms of preprocessing is because, as you saw in the first plots, the range is very different. Here it goes from 0 to 1, here from 100 to 500, here to from minus something to minus 4 to 4. These are different ranges, and this is not good for learning. The network cannot learn like this. So what we do is we do a pre-processing here by shifting, get the mean. Let me show you. Get the mean. This is a simple pre-processing. It can be a better pre-processing, particularly if you have shapes like this that are skewed. But this is it's a simple example here. We get the mean of the distributions, and we subtract the mean. So by construction, it should be at 0. The peak should be at 0. And then, because they have different spread, we calculate the standard deviation of its distribution, and we normalize, we divide the mean of the distribution, each event minus the mean of the distribution over the standard deviation. So it will have like a standard deviation of 1. So all input variables have the same shape. They're centered around 0 and have the same shape, or roughly. So this is what we do with the preprocessing here. Okay. And then what we discussed, we have to create the graph. And here, for simplicity, we create a fully connected graph. And each node of the graph has 4 features: eta, phi, energy, and the transfer momentum. And here is actually when we connect all the form edges between all nodes of the graph. And here, again, this is the x. This is the index, because you remember in the beginning we have the adjacency matrix, so we have to form the adjacency matrix, the connections between the nodes. So, and this y here is the same as we did for the convolutional neural networks. This holds the labels. So each training example, each jet, each object has is signal or background. And this is that convention in PyTorch geometric, how we build the graph and the edges of the graph and the labels. And then we have this data list. Here is a collection of graphs. And then we want to define the GNN model, right? So as we said, the very powerful technique is actually to run convolution of graphs. So you don't have to develop from scratch this involved convolution operation that I described briefly, and I'm happy to answer questions if you have. There is a function in PyTorch geometric that does more or less what we described in the slides. So we start as an input, each node has 4 features, these 4 features here, okay? And then we have a linear transformation of these 4 features to get 32 features, non-physical one, in our abstract space. And then we have a second, so we stack another convolution layer, and we go from 32 features to 64 features. Okay, convolution can be stacked, as we did in the case of the 2D image that we had different, you remember in the example, that we have different filters to extract different features in the image. This is actually what we are doing also here. So these 2 lines are the convolution operations. We have 2 convolution operations in the graph, and then we extract features, and here we want to exploit the correlations between the extracted features. So the input is the channels that we have here, then it's 128, the output, and then again, since it's binary classifier, we have 1 output node, and then we have the sigmoid function. And we do a global pooling here, mean pooling in this case for the graph. We don't get the max, but you can play with this thing. This is the activation function and the sigmoid. These are things that I think you discussed also in the introduction yesterday. So let's define the graph. And for those that like more the mathematical language, this is effectively the operation the convolution operation that is done at the graph level. Okay, so H is the feature vector of node I at the convolution layer L, so it will be in the first layer or the second in this case. Then N here, so we look, the J runs over the neighbors of the node I, okay? This is defined by the KNN. This is the number of neighbors that we want, and these are the learnable parameters, the weights and the biases for the first or the second layer here. And sigma here is the activation function. Okay. Okay. So let's build the graph, and visualize the graph. So this is just a bit of technical. We use the information from, we build the graphs here, and you are going to see how a graph looks like. Now, since this will take some time, so let me take, let me look the Q&A. Sorry, what is? Okay, I don't know why the error. I'm not sure why you're getting this error. If we do a fully connected GNN, would this not be equivalent to corresponding fully connected? Yes, but you don't have the convolution operation there. It's not exactly the same. Because then when you run a convolution, a fully connected graph, you start bringing closer. It's much, much more efficient to exploit the correlations than using a fully connected neural network. In principle, you can do the same thing, but then the number of parameters explodes. You need to stack very many hidden layers to get this. And this is a simple graph, and yeah. Is updating the graph from H fees essential as embedding the relation with No, you can skip updating the graph. You can skip updating the graph, but it gives you, depends on the task. In this task, it can give like a 10-20% improvement in performance, like in the background rejection for the same signal efficiency. But it's not. Yeah, you can skip it. Particularly if you want the algorithm to run faster, yeah, you can skip updating the graph. We pad the number of constituents because the jets have on average, let's say 50 or 60 or 80 particles, but there could be some jets that have 110 or some others that have 50. So this is the reason why we pad them. Now, in PyTorch geometric, you don't necessarily have to pad it. It's a dynamic network, that's true. If you want to use ONNX to deploy it, then unless there is an update, very recent update, ONNX cannot handle, if you are like in the LHC experiments, ONNX cannot handle PyTorch geometric, so you need to do it pure PyTorch, so then you have to pad. So let me go back. So this is just a visualization. It doesn't tell you much. It tells you about the edges. So here you see this mesh here, and you see there are connections that are further away. But if this visualization is usually if you want to do like to define some rules how to connect particles. It's even cooler to see how the distances get updated as you run convolutional layers. So here we provide the code so you have the machinery to dig deeper here. So this is how a signal events look like. This is how a background graph looks like. Here we prepare the data for training. Again, we split 80%. We use 80% for training, 20% for testing, and batch size 32. And here we run the graph, and we use the same loss function as before. We run for 4 epochs. This will take a little bit more time. Someone asked about the loss, so we get the average loss depending on from the different batches. So this will take a little bit of time, the graph to run. So in the meantime, I can take some questions if there are. Is the node size? What do you mean, node size? The number of nodes or the number of neighbors? I lost this question. You are answering, okay. The hidden side, okay, yes, okay, thanks, Lazar, okay. Yes, the hidden side is a hyperparameter. This guy here, you mean? Yeah. This is the feature, yeah. So already it gives an indication. You remember when we were running the CNNs, we were having actually values, the loss function around 60, 60 something, but never below 0.6. Here you get below 0.6, 0.57. And so this is the loss as a function of the number of epochs. So we run over 4 epochs, but so this tells us an indication that actually probably the graph neural network does better. So, but let's look at the metrics. So here I'm going faster because this is things we discussed before. So we evaluate the model here. We are going to plot the output distribution for signal and background jets of these objects. And you see by eye, look, the CNN was like this. So very little separation, if anything. I mean, very little. It's not any, or some. It's not a random guess. But here, by eye, you see the blue is more distinct than the red. Okay. Although you cannot judge by it gives you a feeling. What will actually tell us if we want to quantify this is to create a rocker. And for the CNN was around 0.58, close to 60%, the area under the curve. Here it's more than 75%. And you see it by eye, you can get like for instance, a 60% true positive rate for a bit more than 20% false positive rate. It's not great, but we just ran for 4 epochs and just 10,000 events. Here, if you go to the CNN, for 60% missed true positive rate, you get more than a factor of 2 higher false positive rate. So this is already a very important gain. So we stop here with this first exercise, and then we're going to the second task. So we'll start with a theory, and then I will pass it to Lazar to discuss the homework, the hands-on exercise. So let me stop sharing and go back and share the slides. So are there any questions, pressing questions? So Lazar, you are taking care of the questions, right?
Right, I'm taking care of as many as I can.
Okay, but we can take if something. But let's go ahead, and then we can come back to the questions. Okay, let me share the slides. So, you can see the slides, right? Yes. So exercise. The second exercise we want to discuss today in this module is about clustering. So clustering, we said, is grouping entities. Could be particles, could be energy deposit that share common features or properties. So let's see. Let's take a step back. So this chain here. I mean, again, don't have to go into the details, but this is how the chain we follow to reconstruct the event. So this guy here is what we were working now the past hour or so. We want to identify the type of this particle here. So the Z type. But what we want to do now is to get a bit lower level information. This is a raw image of how the detail. There are beams, they collide, and we have signals in different parts of the detector. The different colors correspond to different parts of the detector. So what we want, this is what the absolute raw information. The second step is to go in each of these different detectors and group the signals that come from the same particle, let's say, that was produced here. Okay? So this is a clustering problem. So this is much lower information here. So here we want to explore artificial intelligence to group signals, energy deposits in the detector. So when we have a particle that transfers the detector, it produces the signal that you see here. So, and we want, as I said earlier, we want to cluster deposit corresponding to the same particle, right? And we are going to use a very novel and very ambitious detector project. So this detector is not yet installed at the Large Hadron Collider. It will be in a few years from now. It's called, for those that are interested in LHC physics, this is the high granularity, the CMS high granularity endcap calorimeter. This is mostly made of silicon, has more than 6 million channels. So effectively, this is the image you get, or we will be getting when we have this detector at the Large Hadron Collider installed at the CMS detector. So the different colors, here we cheat, we use simulated events. We know from simulation that which particle, where each particle deposited energy. So the different colors correspond to different particles, right? So there is huge potential. We can actually identify each individual particle. But of course, you see here, there is a mess. I mean, it's very difficult to group these particles because there is so much overlap. So if we just use the physical properties like distance and energy, it's very difficult. But it has huge potential. So this is where AI gets into the game. So we have, let's say, I made this sketch to demonstrate what we want to do. This is what we have, the physical space. If we just go here and use the information that we get from the detector, things overlap. Imagine that the different colors here and shape corresponds to the deposits from different particles. So we use a graph neural network-based algorithm that would allow us, we will transform these physical properties, these properties in the physical space, like spatial coordinate, to a new set of coordinates or features of properties that allow us to better discriminate the deposits from different particles. And then, instead of doing, exploit the correlations, etc., we are going to cluster. It's easier to cluster. Define the clustering algorithm to group the reds with the red, the green with the green, the blue with the blue. Here, you see, if you try to group the blues, you are going to have also some red, right? Because you cannot find an algorithm that is so fine-tuned to discriminate red from blue. So just a couple of points. Like clustering is, in contrast to what we're discussing before, which is a fully supervised task, clustering is typically unsupervised, or maybe there is some small, weak supervision. The idea is that we divide a set of points, entities, elements, particles, etc., in groups with similar properties. And the goal is to identify inherent structures and patterns within this dataset without having to label the different, without having to tell the algorithm that this is blue, this is red, this is green, okay? Or use as little as supervision as possible, okay? So at its core, it relies on some sort of a similarity measure, like how similar are the properties between the blue, the red, and the green. So, and another thing you have in mind, you remember when we want to compare the performance, since we use the ROC curve, the receiver operating characteristic curve. Now, since this is an unsupervised case, we cannot use criteria like the area under the curve, accuracy, etc. So this is more channeling, and of course, it introduces some subjectiveness here. Okay. So this is a sketch. We have like strawberries and apples, etc., and we want to separate them in different outputs. This is what you do in everyday life, but the concept is the same. And I think here, for simplicity, this is not what we will use in real life, but since we are, we have a limited time, we use a simplified clustering method. It's called the k-means method. So in actual experiments, we don't know how many of these different colors we have. You can have 10, 100, thousands, we don't know. Here, we assume that we know how many clusters we have. This is the number of k, let's say 10 or 5, etc. But this doesn't, you can replace the class, as you will see in the notebook. What Lazar is going to present, the concept is the same. It factorizes. First, we extract features, and then we run the clustering algorithm. So here, we're going to use the k-means algorithm. We partition all data points into n, all the data points, like the n observation, into k clusters, 5, 10, 15,000, right? And each observation belongs to the cluster with the nearest mean. And then the idea is to minimize, again, this is how neural network learns, is to minimize an objective function. So let me just put some sketch. Let's say we have these points here. They have the same color because we don't label them, okay? But they don't come from the same particles. They're deposits from different particles. Let's say that we want to have K3, let's say, initial centroids, the black, the orange, and the red, so 3 clusters, okay? And then the next step is to start calculating the distance of each of these entities here. It can be energy deposits with respect to the 3 centroids. So we can, for instance, calculate the square of the Euclidean distance. The square is going to penalize more those that are further away. We give more importance there, okay? And we start actually, so this is the sense, so we start assigning data points, could be energy deposits, to the nearest centroid and start forming the cluster, right? And then the next step, the third step, is actually to start recomputing the centroids. So these, as I said here, it can be randomly, or if we have some initial knowledge of how the distribution is, we can actually put the centroids closer to where we expect the cluster to be. So calculate the distance, and we recompute the centroid of each cluster so that the mean of all data points, using all the data points assigned to this cluster. And this we do it iteratively, and we try to find the centroid that minimizes the metric that we have here, right? So this is the objective function. We said we have to minimize an objective function. So this we repeat it and update over and over again as long as we minimize this objective function, okay? And this is the key point, is that we have a weight parameter that if the one point is assigned to a centroid, it takes 1. If not, it gets a 0. And we repeat it until the centroids do not move very much. It means we actually, this gives confidence that we form, let's say, the 3 clusters that we were aiming for. So, okay, so yes, effectively the algorithm reaches a local minimum here. And I think here I pass it, I stop here, and I pass it to Lazar.
Okay. So now that we know some things about k-means and some ideas of clustering algorithms and supervised algorithms, let me explain the overall algorithm structure of what we're trying to do. So the data we have is a point cloud, a bunch of points in space, in real space, with an energy attached to them. And what this corresponds to is, say you have a bunch of particles going through the detector, and as they go through the detector, they deposit some energy in a bunch of points in space, right? And you go and you measure the X, Y, Z coordinates of all of these, and that's what you have right here on the right-hand side. So let's say you had 2 particles, right? and they're going through the detector, and it measures all of the energy deposits, and we have all of that. What our data is going to look like is going to look like something like this. It's not going to be color coded because the colors here correspond to which of these measurements are associated with which particle. So in this case, let's say there were two particles. Cluster 1 here, the red, are all of the measurements which are associated with particle 1. And all of the blue here are all the measurements associated with particle 2. So what our goal is to somehow cluster all of this into looking at this data and somehow splitting it into two clusters, which have all of the measurements with the associated particle 1, also all of the measurements with the associated particle 2. And that's what we'd like to do. Now you can imagine we don't need anything fancy really to do this. I mean, Loukas just explained how k-means work. We could try to use k-means on this, but you can already see kind of just visually here that it would not be so simple to get some good clusters that way, because you can see there's some measurements from particle 1 that are kind of in the region that most of particle 2 is, and vice versa. So it'd be kind of hard to do it on this directly. We need some sort of way to separate out all of these measurements and hope to make it easier to cluster. So that's the entire point of us building a graph neural network, right? So we can build a graph neural network which takes as input this point cloud, so all of these vectors in space and all that, takes it all in, and it rearranges all of the vectors, all the positions of all of these points in such a way where hopefully they're separated. All of particle 1's kind of measurements are kind of in somewhere with the rest of particle 1's measurements, and particle 2 is in its own region, it's by itself somewhere else. And hopefully in this new models organization of this data, it'd be easier to use k-means clustering. So that's the overall goal of using a model, using a graph neural network and clustering to try and improve these sorts of results. So this is great, but you can imagine, how do we make a model do that, right? The model can move the points around however it wants, right? Like, how do we make it so that it does exactly what we want? How do we make it so it's putting particle 1 in its own area, particle 2 in its own area? Well, that's where the loss function comes in. So you need to be very careful and use a very good loss function, because the loss function is how you're telling the model to, like, what you're telling the model to do, right? When you're training, you're minimizing the loss function. So the loss function has to encode this sort of information. So the kind of loss function that we want is we want one where connected vectors, so in this case, for example, a red with a red or a blue with a blue, connected vectors get sent to new vectors in the model's output space where the angle between them is very small, right? So that they're kind of pointing in the same direction, the same area, right? So that's going to bring particle 1, kind of into the same direction, particle 2 in the same direction. But this has still one extra thing missing. You have to be careful, is this doesn't say anything about how we're separating the two, right? This is just us bringing them, the connected vectors together, but not splitting them apart, right? So we need another term in the loss which diffuses them apart, the unconnected vectors. So unconnected vectors, what I mean by that is the red and the blue, for example. The red and the blue, they go through the model, they get a new vector, they get a new position in the model's output space. We want them to be far apart, right? So we want something in the loss function where the angle between unconnected vectors is large, right? So we want the loss to be small when connected vectors have a small angle between them, and large when unconnected vectors have a large angle between them, right? Now, there's another thing to keep track of here. So you may notice there are quite a lot of points, even in just this example input that I'm providing here, I'm showing here. There are a lot of examples of connected vectors and unconnected vectors you can think of. I mean, think about all the ways you can give examples of 2 red points here, or 2 blue points, or red and blue points, and you can give a lot of examples, right? So the loss function, if you provided every possible combination of connected vectors, unconnected vectors, is going to be massive. And it's going to do 2 things. One thing is it would take a long time to train, but the other thing it would do, which is more subtle, is it can overfit kind of your model a little bit. So if you are too specific about what you want the loss to do, or if you give it way too many examples for one piece of data, it can be hard for the model to generalize, and it can be hard for the model to really do a good job on data it hasn't seen before, right? So the in-between that we do here is, instead of providing every single possible example of, vectors we want to be in the same area, vectors we don't want to be in the same area, instead of giving every possible example, we give some subset, right? We choose a handful of examples of connected, unconnected vectors that we use in the loss. And this helps us generalize this model to work on unseen, new data, right? New data kind of lets us tune the supervision, how supervised the model is, right? Kind of a balance, a spectrum of, how accurate and precise do you want the loss to be versus how much do you want to generalize it. So this is what makes it additionally more of a weakly supervised sort of model. Now we have the loss, we have kind of a plan on how to build such a model, right? But you have to think now, okay, we have a model, it's reorganizing, all these vectors to make them easier to cluster. But how do we evaluate how good those clusters actually are? They're not going to be exactly 100% right. They're not going to, be 100% all the same particle inside of them. So we need some sort of way to determine how good they really are. That's where we go and we develop some metrics to evaluate how good the clusters are. So the metrics we're using here are purity and energy-weighted purity. So what purity is you just go, you look at the clusters that you made with k-means on the model output, and you just see how much of that cluster is made of the same particle, right? If cluster 1, which is supposed to be particle 1, has 95% purity, that means 95% of the measurements inside of that cluster are particle 1, right? Energy-weighted purity is very similar. Remember, these are energy deposits, right? So these aren't just, points in space. They also have an energy kind of associated with them, an energy deposited there. So energy-weighted purity is kind of doing purity using the purity metric, where you count, you see how much is made of the same particle, but instead you do it with the energy. So how much of particle 1's energy is that cluster made up of? How much of particle 2's energy is cluster 2 made up of? So if you have a 95% energy-weighted purity, that cluster has 95% of the whatever particle 1's energy, right? So now this is kind of like the general overview now. Now we have kind of everything. We can go evaluate the metrics on the input itself. So we use k-means on the model input. So just like the raw real space input, we look at the, how good are the clusters by looking at the metrics. And then we can go run that input through the model, have it move the vectors around, hopefully make it easier to cluster, run k-means on that, and then see the, metrics there. And if we see consistently better metrics on the model's output, using k-means clustering on the model's output, then that should indicate to us our model's good. Our model's pretty good, right? And that's the general overview of what we're going to be looking at in the exercise. I don't know if I have some Q&A. Is it here? Keep seeing this pop up. I don't think that's it. Is it over here? Ah, here we go.
I will.
Sorry?
I'm taking care of some of.
Oh, okay. Okay. So here, let me just go straight to the notebook. Oh, I can see some of them. Okay. It's hard to tell which of these are from the previous part and which from the part I'm working on right now. So I'm going to get back to some of these in a second. Let me just see if I can X that out. Okay, so I'll let everybody open the notebooks if they're following along. Real quick. Okay. So much like Lucas's notebook, we need to start off and install some required libraries. So these are just going to be some libraries that are just necessary to, run the training, build the model, do a lot of the stuff that we're doing. And then we go through, mount your drive. I already have mine mounted. It's going to pop up and say it needs authorization, whatever else. You're going to need to give permission there. Once you have that done. Okay. So these are just a bunch of libraries that are going to be useful for building the model and k-means and stuff like that. Loukas also used some of the same libraries in his notebook. Okay. And then to load the data, we need to pre-process some of the data. This isn't too important. This is just for loading the data. So I'm going to go straight to loading the data here. So make sure your paths here are set up correctly. Just make sure that you have these paths available. You have access to the Google Drive. And if you don't, go over here, click on Files, and then you can see your drive right here. And you can scroll through that and see if you can find what the actual path is, if yours is for some reason slightly different. But it should be somewhere in there, and it should be quite easy to update. But I'm pretty sure this is the standard we have here. So we can go and run that. This is going to load the data. So now all we're going to do is I just have something here that's going to plot out what an example of the data looks like. So we saw this already in the presentation, but here you can see in this example, in this case, we have 5 particles. All right, so we have 5 particles. The X and Y and axis are kind of like the detector itself. This is like a bunch of detectors set up along the same axis. So the Z-axis is the kind of along the detector axis, if you want to think of it that way. And the XY is like the actual in the individual kind of detector. So this is kind of what we're looking at here. So you can see even from here, if I were to take off all of these colors, it'd be really hard to it'd be really hard to know, how to color this in 5 different ways. So this is essentially why building this sort of model is going to be really helpful. Is these things can get really, really, shaken up and kind of everything's everywhere. It's hard to tell what's going on. So now we can go and build the actual model itself. So we're using graph neural network. So you can build whatever works for you. But let me explain the general outline of what's going on here. So remember, our data is made up of a bunch of points. These points are just vectors, just a list of numbers, coordinate, and energy, whatever else is associated with those nodes, those vectors, right? So what we'd like to do is we'd like to get a better representation of these vectors that the model can kind of use to, learn and do everything it's doing. So what we're going to start off with is on each vector independently, right? So on each vector independently, we're going to have a dense, connected layer that's going to just bring up the dimensionality to some number. This is a hyperparameter. So this is something you can choose and change in your algorithm when you're optimizing it. But right now we're just bringing up the dimensionality into a higher dimension so that the model can kind of work with some more stuff. So I'm using 32. So I'm bringing it from the original, X, Y, Z, the energy, all of the angles and all that. I'm bringing that up to 32. And we apply this independently on each vector, so this has nothing to do with, taking into account what's around them or anything. This is just bringing up the dimensionality. Then we go to the actual, the graph part where we use dynamic edge convolution. So what we're doing here is now each of these nodes, right? So each of those vectors now go through and you look at some of the neighbors. That's another parameter that I'm using 30. You look at the 30 nearest neighbors and you aggregate them in some sort of way so that the new value of the nodes, so the new value of the, points, are not just based off of whatever the original values were, the coordinates and all that. But it's based off of also what's kind of around it, right? So this is the part that's kind of like learning about the shower itself, right? So this is where we introduce that sort of concept. And you can run that a few times. You can do several iterations of this. You can decide how many times you want to do it. The more times, the more complex the model. It'll also be harder to train. There's a trade-off there. But once you go through and do all of that, we now need to, kind of similar to like what we started off with, where we were bringing the dimensionality up. Now we run independently each of those vectors, each of those nodes, through some more dense linear layers that are just there to kind of take the dimensionality of the vector and bring it to whatever dimension you want the output of the model to be, right? If you want the model to take in a vector in real space with whatever, 3 values, 4 values, 7 values, and whatever your input looks like, and you want it to output an 8-dimensional vector, right? You want to have it output whatever dimensional vector you want. That's the output dimension parameter here, right? So this is something you can also play with. If you have a larger value, maybe your model will have more room to kind of move things in, but it'll also be harder to train. That's another thing to play around with, but that's the overall idea of the algorithm, of the model right there. So we run that. Okay. Now we define the loss. So what I explained earlier is a general idea of what you want a loss function to do, right? Or that's the general idea of what we want the loss function to do. You can think of many ways of accomplishing that, right? So what I'm doing here is I'm taking in all of so I have some set of examples of connected, unconnected vectors, right? That are the same connected ones are, 2 nodes that are supposed to be the same particle. Unconnected ones are supposed to be separate particles, right? I'm taking this information in, and I'm just calculating the cosine similarity between the connected nodes, right? So the cosine similarity is large when the vectors point in the same direction or near almost the same direction, right? So if we take the model's output of 2 connected vectors and the cosine similarity is large, then we want the loss function to be small, right? So that's why there's a minus sign here. And that's going to help us, train the model to push the same particles together to have the dispersion of like non-connected vectors, unconnected vectors, right? The ones that are not connected, separate particles. We need to have a cosine similarity, or I use a cosine similarity. You can use something that gets the job done, but I use cosine similarity of the unconnected vectors. So I have my examples of unconnected vectors, a red one and a blue one, as in the slides that we were looking at. And I look at the model's output for those, and I make sure that the cosine similarity is very low when like that's what I want to push the loss function to do. I want the loss function to be large when the cosine similarity is large, and I want it to be low when the cosine similarity is low. That's why this doesn't have a minus sign. Then you can add these together, and depending on how much you value each of these aspects or whatever way, whatever helps the training the most, you can kind of scale it up. So you can scale one of them more than the other. So that's why there's this temperature term here. If you want to, for whatever reason, bias towards one of these more than the other, you can do that. So we can run that. And then now we have our training. So the training of the model is going to be much like every other model you're going to train with. You start off by, looping through all of your data, all of your batches. You're going to go through, you're going to see what the model's output is, right? You're going to see what the model's output is for that specific data you're looping over, your training data specifically. Then you're going to extract the information that's necessary to know which are the connected pairs, the unconnected pairs. You run that through your loss function, which we looked at earlier. You run that through your loss function, you save the loss function, and then you update the model to minimize the loss. So you saw what the weights and parameters and biases of the model give you initially, you take the loss, you update the weights to minimize the loss. Right? So that's one epoch, is just running through all of your training data and doing this sort of process. And then we have a testing loop as well. It's going to be very similar, just here we're not going to be updating. We're not going to be updating the weights. We're just looking at evaluating the loss on the validation data. So on the data the model is not being trained on, we want to track that while we're training so that we can see if it starts overfitting. Because if the training loss keeps going down and down and down and down, but we see on testing data or validation data that the loss is no longer getting better. So on data it's not being trained on, it's no longer getting better or it's getting worse or something like that, we want to stop the training, right? We don't want to overfit our model. So it's going to be very similar, just not going to be updating it. It's just going to be saving the losses. And then, so over here is, so there's going to be a lot of code with just loading the model, saving the model, printing things and all of that. But the important things here are just going to be, here's where you specify the architecture of your model, right? So here, input dimension, that's just the dimension of the data itself, like the vector, in one vector in the data itself, right? So don't touch that. But here, hidden dimension, so that's the dimension that you bring it up to in that first sort of step of the model, where you're kind of increasing the dimensionality so the model has something more complicated to learn of. And then you have K. So K is, remember, once we have our point cloud and we kind of brought the dimensions up of each vector individually, now we want to learn something. We want to have each node, so each one of those vectors, kind of learn something about what's around it, right? So in this case, I'm using K equals 30, which means we're taking information from the 30 nearest neighbors when we're going through that sort of dynamic edge convolution step. Latent vector is the dimension of your output, right? So that's the dimension of the vector that the model is going to give you in the end. It can be the same as the input if you want. It can be larger. It doesn't matter because it's just a list of numbers, right? You can cluster on a list of numbers. It's just a bunch of parameters, right? So if you use a larger number, your model may be harder to deal with, but it's also, or harder to train, I should say, but it will also maybe, if you have a lot of different kinds of particles, like 1 million particles or something, let's say, I'm just saying a random number, then maybe having a larger size dimension vector will kind of give it more room to separate things out properly, right? So there's a balance there to try different things, but I'm using 8. 8 worked in this example for me. So we can go ahead and run that. So now remember how I said that we have the connected vectors, we have the unconnected vectors, and we can't look at all of them. So we have to choose, some subset to use in the loss function, right? So each time you go through, and you can run this right now, each time you go through and get the data, it's set up so that we choose randomly some connected and unconnected vectors to use in the loss. So that takes a little bit of time. So what we're doing right here is we're just kind of caching it so we can save some time and just kind of like save one set of examples that we can kind of run several epochs for, and then update it again later, and then so on, right? So now we're just loading that data. So over here, this is where your model's information is going to be saved. So when we go start training, matter of fact, to run this right now, so start running this right now, you don't have to use 75 epochs. Try something maybe like 25. But start running this right now, but this is where your model is going to be saved, right? So this doesn't have to be in the drive or anywhere. It can even just be here in Google Colab or wherever it is. So this directory right here, for you should say local path plus M3 or something like that. This just save this wherever is most convenient for you, because you're not extracting anything here. This is just where it's going to save the information about the training and stuff like that. So now we can go through. So let me explain a little bit about here. So now we're actually going to start the training, right? And here are some of the parameters that are going to be useful in the training here. So this is the learning rate. So this is, Loukas mentioned this earlier. This has to do with how large kind of the updates are. So when you're going and you're training the model and you're changing the weights to lower the loss and make it better and everything, the learning rate here is associated with kind of how large those updates are, right? And Loukas also mentioned that you can have a weight decay, learning rate decay, and that's exactly what this is right here. So these are parameters related to the weight decay. So what this is saying is every 25 steps that the model takes, multiply the learning rate by 0.95. So it's slowly going to scale it down so that it becomes, as the model kind of learns the general stuff at the start and then starts learning the finer, more detailed aspects, it's going to have a smaller update. So it can kind of really fine tune itself and hopefully find those local minima, the bottom of them as best as it can, right? So I use 75 epochs here because I wanted to show you guys, what it would look like. But for you guys, if 25 should be fine, 5 should be fine, some smaller number should be fine to run, but it will just gradually get better and better and better. So let me show you an example of, so you can run this. I already ran this just earlier. What you're going to see is you're going to see several things. So you're going to see the epoch that's running at the time, the training loss. So this is the loss on the data it's actually training on, what it is for that epoch. The validation loss. So that's the loss on the data that it's not trained on. Right, so this is kind of us to evaluate if it's overfitting, and then the learning rate. And if you need to mess around with the learning rate and you see it's jumping around too much, go ahead. And you can see that it's decreasing here each epoch, right? So let me show you what so while you guys are running this might take a couple minutes, but let me show you guys what 75 epochs of running this would look like, or 70 or so. So here the blue line is the loss of the training on the training data, and the other color is on the testing data. And you can see, here, it's more jagged and all that. It's again because it's not the data it's being trained on. So and also depending on your parameters of the learning rate and whatever else you're using, it may look like it's moving quite a lot at the start, but then it kind of levels off. If you use the lower learning rate, it would be much smoother, but it would take longer. So find whatever balance works for you. If you change the batch size, right, like Loukas was talking about, it's another thing you can optimize. You can change the batch size. If the batch size is larger, it will take up more memory, right? We're only using a batch size of like 10 here, but it will give you more accurate steps because you're using more of the data to evaluate the loss before you update the model, right? And if you use a lower data size, you're going to be able to do more updates because you have more batches, right? Because smaller batch size. But the steps are going to be a little bit more inaccurate. So once you have everything there, you can go and load the best model. So the best model is going to be the one with the lowest validation loss, specifically, not the training loss. So the one that had the best loss on the data that was new to the model, right? It was never trained on. So you can go, we can load that. This is just loading up the data. And now we have a trained model, right? So now all we need to do is just, set up the, stuff around plotting and evaluating the metrics. But we're kind of ready to see how well this is doing, right? So this is a lot of just, setup for the plotting and of the clusters and all that. But the important thing here is if you have a clustering algorithm, right? So you go here, right? So if you have a clustering algorithm, here we're using k-means, and we're doing two separate kinds of clustering. So we're doing one clustering with the number of clusters, which is what you have to specify, being the true number of particles, right? So if there were 5 in that, example you were looking at, the number of clusters would be 5 on the model's input, right? So this is doing k-means clustering on the input itself. before it even runs through any trained model or anything, right? There we go. We see the labels there. We see, how that separated things out and how that gave us clusters. And then we do another clustering. So we do now clustering on the model's output, right? Same thing with the number of clusters being the true number of particles. And what we do is we first run it through the model. So we have the model give us, takes the original input, the original point cloud and how everything's set up, gives us a new vector for everything, hopefully organized it right if we trained it well. And then we get those labels, right? And then we can associate, and see how k-means clustering on the output, if it's any better, right? So we can go ahead and run that when you're ready. And then now this is just some plotting code for visualizing the clusters themselves. It's similar code to what we used earlier to look at the data, but we're just doing it for the k-means outputs. And now we're ready. So now we can go ahead, and if we run this, what we're going to do is it's going to run through the testing. So here, let me find it. So it's going to run through the testing, loop through. It's going to do k-means clustering on the input of the testing data, do k-means clustering on the output, and then visualize it for you and show you the metrics. So here, let me give you an example here, for example, like here. So let me explain what this is right here. So on the left-hand side, this is the input that we're using, and it's clustered perfectly well. Like these are the true clusters. These colors here are how it's supposed to be clustered, right? And the right-hand side is how k-means clusters on the input, right? K-means doesn't know what the true labels are, it just sees a bunch of points with numbers associated with them, right? So this is how it clusters. You can kind of see it just kind of splitting it up into a pie chart, kind of what you'd expect based off of how we explained how k-means works earlier, right? And you can now see, if you wish, all of the information about the purities of each of those clusters and stuff like that. But we can now look for the same exact event, right? So this is the same exact event. This is what, the algorithm predicts. So if you were to use it on the algorithm's output, so it's not so visually clear, but you can see already that it's doing something a little bit more sophisticated, right? You can see that it's not just kind of splitting it up into a pie chart, into, Simon Says puzzle or something. It's doing something a little bit more sophisticated. So it has the ability to do something, do some more complicated clustering. So we can see another example here. It's on the input, it's on the output. And if we go through and look at the average values of these metrics on the input, so the input's like 20-something%, averaged out over this testing data, but you can see k-means on the output. So when you use the model's positioning of everything, and then cluster on that and see what the labels will be, you can see that there's a significant improvement in the metrics here. And if you give it more data and you optimize you run it for a longer amount of epochs and you tune the model just right, and you can push this quite high. You can really make this separation quite strong. So that's kind of the overall idea of the entire algorithm here. So you can go back and, once you're done running through the notebook, you can go back and find those hyperparameters of the model. So how many times you're doing the edge convolution, right? How many times you're doing the graph part, where it's kind of taking information from the entire neighboring nodes and aggregating it, or how many nearest neighbors it's looking at, what the dimensions of all. You can play with those hyperparameters and see how that affects this sort of performance here. But here you can clearly see that both visually, you can see that it's able to do something more complicated than just, what's possible with the raw input, but you can also see the average metrics indicate that on the testing data, yeah, there's a significant improvement here. And that's the overall notebook. I guess I can look at some of the questions, if there are any questions. Here. To train on polarization. Sorry?
Just while you're reading the questions, I just wanted to point out we sent a broadcast into the everyone chat. The version of the notebook that people are downloading does unfortunately have a mistake in the path definition that may be making it difficult for people to run it. We will fix this after the presentation, and the new version that gets posted into the shared directory will have that fixed so it can be executed.
As far as the directory, it should be the same one in Loukus's notebook. So if Loukus's notebook is working for you, it's in the same exact.
I know.
Place.
Unfortunately, there's a mistake inside the code further down that is causing a problem. For those people who understand virtual machine and the directory structure, they may be able to patch it themselves, but we will also patch a version. We will post a version. The machine learning is great. It's just the directory structure is actually not working.
Okay. I hope it can be solved easily. If it has anything to do with this directory doesn't need to be have anything to do with the drive. You can just set this. You can just set this to be just the current path. You can get rid of all of this stuff to the right. You could just set it to be the current path, and now or current path plus /m3 or something, and it's going to make a directory here and save all of that sort of information there. So if it has something to do with this, then don't worry about saving it in your drive or anything. You can just save it here, just current path plus /m3 like this, plus /m3. And if that works for you guys, then that should be good. But other than that, the other directory should be the same as Loukus's. Sorry if there's some sort of strange thing going on over there, but hopefully those fixes can help with that.
Loukus's code was fine. Let's just focus. I just wanted to raise it in case anybody was puzzled. Let's focus on the machine learning, and as you say, we will after the presentation, we'll make sure that the version 3 that gets uploaded actually has the has a path system that works without people having to modify it. Yeah.
Okay. So let me see. Yes, this is a great point. Yes, absolutely, Ralph. That's exactly right. That's a great point. Introducing the intention mechanism would be another great way to really improve the model. Yeah, that's right. Is there a module to submit? When is the deadline? Looks like some of the questions were answered, I believe, by Loukas. How to de-channelize. Looks like it's just a bunch of questions about the path. But yeah, if there are no other questions, that's the general outline over how to run this. Is there anything else to address? Answered maybe? Okay, well, thank you for, oh, another question. Are we submitting anything for this module? You can submit for Loukus's module the area under the curve number, I believe. But if you want to submit something for this module as well, this chart right here, so this graph right here, this image would be what I suggested.
Sorry,
sorry, Rick. Yes, please go ahead.
Sorry, you can only make one submission per module. So you which one?
Yeah, then Loukus's area under the curve one.
Yeah, there is in the shared folder there is a Google form, right? Or where there are the other Google forms, there is a form corresponding to this module, and then you will run for 10 epochs the graph neural network and submit the area under the curve, the value of the area under the curve. So it's one value, just the number, the decimal number, please.
The submission form is linked in the README file at the root level of the shared drive. For every module, if there is a submission, you can do it via that. Maybe, Loukas, you could reiterate exactly what you want submitted.
Yeah, so to run the classification task using the graph neural network approach, instead of 4 epochs to 10 epochs and submit the area under the curve, that it will pop up in the rock curve in the lower right side of the rock curve if they run the notebook. So this number there. And we will see how it fluctuates, etc., across the participants.
Right, so I don't have more to present, but I can answer anything else I see if there are new questions. Oh, Loukas, can you share screen to show exactly what the task is? Somebody asks.
Yeah, it's just, sorry, and it, yeah, because I closed the book. So, so if you run the steps, you get the rock curve, and this is the area under the curve, the value of the area, I mean the integral here. So this is for 4 epochs, you run for 10 epochs, and you get a number, so submit this number here. Only for the GNN, yes. Deadline, I mean, you can, yeah, I mean, the sooner the better, I mean, I guess by the end of the week. Find where to define the number of epochs and change this from 4 to 10, run the steps and get this number on the lower right part and just put it in Google form. This is written on the Google form. This is written on what to do.
Okay, we could draw to a close there unless you want to. Are there any other questions you particularly think are useful to to address in the Q&A? Otherwise, we can stop there.
Yes. Done. Ralph, I don't understand your question specifically there, so I don't know how to answer that. Sorry.
Well, just concerning the ResNet model, which is a 2D model or a ResNet type like 1D, we compare with graph neural networks, and graph neural networks do better in classification tasks than the ResNet 50 model. Now, autoencoders, yes, we use, but in other tasks like anomaly detection, etc. transformer models, which is like LLM, like we use for jet identification, and they bring some gains because at its core is it's an efficient way to process a fully connected graph, the transformer. So yes.
Okay, are there any more questions, or should we draw to a close there? Okay. Well, Lazar, Loukas, if we could thank you both again very much for an excellent presentation. As I said, we will just patch the version of the code that is live on the shared directory. Obviously, those of you who understand the Unix file structure, you probably already patched it yourself, but we will provide a fix so that for those of you who are less familiar with how to manage directories. And otherwise, we'd like to thank everybody who participated, and thank you for the questions. Appreciate those enormously. Okay, so we're going to end this presentation, and then we will be back up again, which is Eastern time is 2 p.m. In the afternoon, but obviously that's US Eastern. I hope you may have seen the posting we made. For those of you who would like to understand the time zones, the schedule can be set to whichever time zone you're currently in, but obviously we're always, in absolute terms, we begin the next broadcast to Zoom at 2 p.m. US Eastern time. But if you use the feature, the menu in the top right-hand corner of the Indico schedule, you can see the live schedule in whichever time zone you're in. I from memory, I think you have to have logged into the Indico using your the ID that you used for your original registration in order to make use of the time zone feature. But otherwise, you can just Google the time zone change. But 2 p.m. Eastern later today, Tuesday. Okay, thank you very much, everybody. So I think at that point, we're going to stop the broadcast until 2 p.m. Eastern, which is about 1 3/4 hours from now. Thank you.
Thank you, and enjoy the rest of the workshop. Bye-bye.
Yeah, enjoy. Thank you.